Hello everyone. In this video we are going to discuss another topic, that is hysteresis. When we take a magnetic material and when we change the magnetizing force by changing the magnetic field. So when we change the magnetizing force, we see that there is a change in the intensity of magnetization also. But they don't go side by side. We will see that there is a lag in the intensity of magnetization with the increasing or the decreasing value of the magnetizing force. They don't behave exactly in the same way, the way they have started initially. So there is a lag between them, and that is known as hysteresis, and that we are going to study. We will discuss a loop. That loop is also known as hysteresis loop. So let us see here. The topic that we are going to discuss here is hysteresis. Now, to understand this topic, let us draw a coordinate system where we have y-axis and let this be the x-axis. Here, x-axis represents the magnetizing force and the y-axis represents the intensity of magnetization that is given by I. Now here we will take a magnetic material here. Let it be iron. Suppose we take a magnetic material here. Let this be the magnetic material where the dipoles of the atom are randomly oriented. Okay, they are randomly oriented and they cancels each other effect, so the net dipole moment is zero. So in this condition we have not applied any magnetic field, so the value of H is also zero and I is also zero. So this is the point on the origin which we are showing as O, where H and I both are zero. Now what we do is we apply magnetic field, that is magnetizing force in this direction, and say the value of H increases. Magnetic field is increased, so value of H increases. So when the value of H increases, you will find that some of the dipoles have started aligning themselves in the direction of, some are still in the random direction, but at least some of them have started aligning itself in the direction of the applied magnetic field. So the value of I also increases because intensity of magnetization, since they go on aligning themselves, so I also increase. Okay, so we have a graph. The curve can be like this, where we increase the value of H, the value of I also increases. Now suppose we take a condition here where H is increased such that all of them are aligned itself in the direction of the applied magnetic field, in this, that is in this direction. That means if you further increase the value of H, the value of I will not increase. Since I depends on the alignment of the atoms which are behaving as a dipole in this particular direction, so I becomes maximum, it will not further increase. If you still want to increase the value of H, you can increase, but the value of I remains maximum. So if we extend the graph here, so you'll find that a region comes where you'll find that this graph becomes parallel to the x-axis. That means you can increase the value of H, but the value of I has become maximum here, so it will not increase from this value. So the value of H after say this point, if we increase the value of H also, then also it will not have any effect on I. Now let this point be given by A. Now suppose we want to demagnetize it. This is very important. You need to understand it very carefully. Suppose we want to demagnetize it. That is, whatever magnetic property this material has gained, it has to lose this property. So what we do is, the magnetic field or the magnetizing force we apply in the same direction only, but this time we start decreasing it. Instead of increasing it, we will decrease it. We start decreasing it. So obviously the magnetic dipoles which are aligned in this direction, they start deorienting themselves from the actual line, and therefore we can say that I also decreases. But this step you need to understand. When we decrease the value of H such that finally H becomes 0, we will still find that some of them are still aligned in the initial. You can see this one particular dipole which is still aligned in the direction. So the value of I has decreased, but it has not become 0. This is the very important thing which you need to understand. H we have made 0. We have increased the value of H, I increases to maximum, but then when we decrease it to 0, I doesn't come to 0. So the graph, if we want to draw it from here, this will be the shape of the graph. Look at the point here. This point, let it be given by B. OB represents the residual magnetism. That is the magnetism which is still left in the magnetic material even after the removal of the magnetizing force. H को हमने 0 बना दिया, H is 0, but still then we find that there is certain amount of magnetism which is left out with it. This is known as residual magnetism. It is also known as retentivity. Okay. Now still we wish to make the value of I 0. So what we do is, we start applying the magnetizing force in the opposite direction, and opposite direction we start increasing the value. So at a certain point you will find that I becomes 0. That means random orientation is there. So I becomes 0. So opposite direction, we are showing it here. This point, let it be given by C. So OC represents the magnetic field which is provided in the opposite direction, such that the magnetic material loses its magnetism. That is, intensity of magnetization becomes 0. So that particular value of magnetizing force in the opposite direction is known as coercivity. Coercivity. COERSIVITY. OC. OC represents the coercivity, whereas residual magnetism is represented by OB. Now, again we go on increasing the value of H in the same direction, that is in the opposite direction. So we'll find that the value of I will also increase, but now it will increase in the opposite direction. And you will find that we are increasing H in this direction. We'll find that I at a particular point becomes maximum. Then we again want to decrease its value of I to 0. We decrease the magnetizing force. So intensity of magnetization decreases, but magnetizing force becomes 0. Intensity of magnetization is still left out over there. We further increase it in the opposite direction, that is the same direction which we have started with, and at this point we get the intensity of magnetization to be 0. And again we move forward, so we reach the point A. So we started with the graph here from O to A, then from A to B, B to C, then C to D. This point, let it be given by D, then D to E, and finally E to F, and lastly from F to A. Now continuously, if we magnetize and demagnetize the magnetic material, we will get the loop A, B, C, D, E, F, A. This is the loop which we will get, and this loop is known as hysteresis loop. Hysteresis loop. Now, the line or the curve OA, that we will never get again. This is the initial value, initial curve. At the starting only we get this OA curve. Later on, continuous magnetization and demagnetization, we will not be getting this value. I hope this is very clear to you. Now, this OB represents the residual magnetism even after the removal of the magnetic field. So OB is also equal to OE, and similarly coercivity, the magnetizing force in the opposite direction to demagnetize the material, is also equal to OF. So you can see that initially we started with same zero magnetizing force and zero intensity of magnetization, but later on what we see that magnetizing force is zero, but the magnetic intensity of magnetization is not zero. There is a lag between H and I. They initially started equally, but they lag behind, intensity of magnetization lags behind the magnetizing force, and this lag is known as hysteresis, and the loop which is formed is known as hysteresis loop. So I hope this is very clear to you. Now, some of the applications we will quickly see. Let me take another page here. We have just now seen the hysteresis loop. Now, in the hysteresis loop, let us make another hysteresis loop. Let this be the another hysteresis loop. Again, we are taking H here, and this is I. Now, let us take two different materials. One, we are taking it for soft iron, and soft iron, the percentage of carbon is less, and another we take for steel. This is for steel, this one, and this for soft iron. Now you look at the hysteresis loop. Now let us choose certain materials, like transformer is an example we are considering. In a transformer, which we will study later on also, we take a core. This is the core of the transformer which I am drawing, which are in the form of sheets, one taken one after the other. And winding of wire is there. This is the secondary primary coil, and this is the secondary coil where we get the output. Here we get the output voltage, and here is the input. Now, the soft iron, this core is made up of soft iron instead of steel. Soft iron because soft iron having the lesser area of the hysteresis loop, and area of the loop is directly proportional to energy loss or energy dissipated. So area of the hysteresis loop is more, so more energy will be lost, so steel cannot be used. So that's why we have to use the soft iron. So I hope this is very clear to you, but still then if there is any doubt, then you can post me the doubt. Thank you.